Alright, welcome back to another week of fun Mathematical Methods Year 12. Hope that you had a good weekend. Cool, let's get stuck into it. We are talking about the chain rule, exercise 9E. You'll find this on page 375 of your fun textbooks. Now, basically they're saying here, hey, if you had an expression x cubed plus 1, all of that being squared, yeah, if you needed to differentiate that, you could expand it out and then do the process there. Yep, that's all good. However, they're saying, hey, what happens if you have this expression where you've got x cubed plus 1 and all of those to the power of 30? Well, that's going to be a little bit more difficult to expand out. Yep. A lot more difficult, yep, and it's going to take you a long time to be able to differentiate that using traditional techniques. However, the good news is we can actually define these functions, or this one here, as a composite of two similar functions or simpler functions defined by the following. So consider this middle part here in the bracket, if you define that as u, so u as being x to the power of 3 plus 1, and the other part of the composite function being u squared, then what's happening is they're essentially chained together and you've got a composite function like we were talking about earlier in the year. So you've got f of g of x. Cool. What you can do is then apply what's called the chain rule, which we're about to do, to be able to differentiate these composite functions. Yep. So essentially there are two different types of notations here. They're saying here you can find the derivative of q as being the derivative of x of g of x multiplied by the derivative of g of x, yep, the derivative there. I prefer using Leibniz's notation here, yep, where you have u and you also have y, and we say the derivative dy dx is equal to dy du multiplied by du dx, yep. I probably prefer this notation, but everyone's got their choices here when it comes to doing this. Alrighty, happy for you to have a read through that to be happy with how it's all derived. So there's a bit of proof there if you don't believe what's going on. Here is worked example number 21. It says here differentiate. We've got 4x cubed take away 5x, and that's all to the power of negative 2. Yep. So again, I would use the Leibniz's notation, yep. But if you prefer to follow along and you understand this way better, ultimately it's the same thing that you're working out here, yep. So I consider the part in the middle here as u. So making u as being 4x cubed take away 5x, and then obviously y is equal to u to the power of negative 2, yep. So I've listed each of those. First of all, we're going to find the derivative of this here, yep. So we're going to find out dy du. In this case, like we were doing before, negative 2 comes down the front. When we take away 1 from the power, negative 2 take away 1, we've got negative 2u to the power of negative 3. Cool, we've got dy du. We're also going to calculate du dx. So following that process, 3 times 4 is 12, x to the power of 2, we've taken away 1 from the power. 1 times negative 5 is negative 5, take away 1 from the power, we just end up with x to the power of 0, which is this here. Yep. So we now have du dx. Yep. Using Leibniz's notation for the chain rule to find out what dy dx is, dy dx is dy du multiplied by du dx. So here I've written out dy du, and we've written out multiplying this using the dot here is multiplying dot 12x squared take away 5, so du dx, they've written it out. Then the last thing we need to do is just make sure we actually substitute in back what u was. Yep. So where u was, it's 4x cubed take away 5x. Yep. Again, making sure that we rewrite things with positive powers. This will go onto the bottom line. So u to the power of 3 goes on the bottom line, and we substitute in obviously what u is here. Yep. And notice it is the same as with the other notation there. Same difference. Cool. They're suggesting that you can do this type of thing on your calculator. So again, you could define g of x and defining h of x, and then defining the composite function here, as f of x as being g of h of x. By doing that, you can then find the derivative of f of x, and it will work out like we just did before. So feel free to have a bit of a go of that. Last one here, we've got example 22. It says find the gradient of the tangent to the curve with the equation that's listed here at the point 1,4. Again, what you do need to know is this is really the same as 16 multiplied by 3x squared plus 1 to the power of negative 1. Yep. So again, if you consider it in that notation, then the u part is obviously 3x squared plus 1. You are also left with y is equal to 16 u to the power of negative 1, as I've said. From there, once you've got u and you've got y, you also need to find out du dx, so derivative of this. You also need to find out dy du, which is the derivative of this part here. And notice the way it's good to set these things out and clearly write out what is u, clearly write out what is y, clearly write out what is du dx, clearly write out what is dy du. I still always write out the chain rule. Dy dx is equal to dy du multiplied by du dx. Write it out carefully. Substitute in these things. We know what dy du is. Write it out. Multiply by the dot. Multiply by du dx. Write it out. Substitute things in. So where the u is, we're substituting this back in. It goes there. And also note that u to the power of negative 2 can go on the bottom line of the fraction and be written as a positive power. And then obviously you've got the 6 multiplied by 6x multiplied by the negative 16 that's on the top line, which is there. Some people might be just tempted just to leave what the derivative is. No, make sure you answer the question. It was actually saying what is the gradient of the tangent at this particular point. So when you've got the derivative or the gradient function, you can find out what's happening by substituting 1 into the derivative, and that will tell us what is happening at x equals 1. At that particular point, substitute 1 into here, we get the gradient at that particular point is negative 6. So let's get a negative gradient at that particular point. Cool, nice summary section. Nice questions for you to have a go at. Cool, bye for now.